Good evening, everyone. My name is Rajat Buni. I am from IIT Dhanbad and I am one of the PMR research scholar at IIT Dhanbad. I am taking this ground improvement uh, lectures, which is conducted by Nptel team and taught by Professor Dilip Kumar Boindo sir. He is a well-known person at IIT Kharagpur. I am one of his TA regarding this course, and I am discussing this week 7 lectures in this session. This session is about 2 hours, and uh, I think it is already 8:13, 6:13, and I am start now. And if I think the slides are visible to everyone, and I already also the sound also clear to everyone. And I'm starting today's lectures regarding this ground improvement. And I want to clear on 2 3 points. My network is creating some problem, and please, if any issue regarding this my network, please don't leave this session. Keep on this meeting, and I will try to rejoin this session. And another thing is this, whichever I am discussing in this session is we will share to you through Google Drive by Nptel team, and also this video is recording, but also uploaded in my YouTube channel, and you can access it through Nptel team. And now I am starting today's lectures, and let's start. In previous weeks, up to week 6, we will discuss up to dewatering and drainage technique. One of these, like any other ground improvement, it is also one of the technique. And today we discuss another new topic, which is called pre-consolidation, which is also related to this drainage and dewatering technique. But in this pre-consolidation, we use the consolidation method to improve the ground and or increase the strength and stability of the ground. So we know that we did in two methods in geotechnical engineering, basic geotechnical engineering, we studied that by two methods we densify the soil in or ground by two methods. One is compaction method, another one is consolidation method. In compression method, uh, we uh, we actually expel out the air void, and in consolidation, we actually reduce the water voids or water pores. So both are used to densify the soil, but the compaction method is very quick, and it is mostly used for cohesionless soil. But the consolidation method is a lengthy process, and it is used for the cohesive soil, or we can say the fine grained soil, or silty sand, silty clay, or clay soil. So by this technique, so already by this name pre-consolidation, we actually use the consolidation technique before the construction of our structure. So, and we know that consolidation method is used for the mostly for the clay soil or cohesive soil. So this technique is mostly suitable for the cohesive nature of soil. So now we discuss about the basic concept of the consideration pre-consideration method. So in pre-consideration, we apply the preloading, or we can say the surcharge on the ground to generate the excess pore water pressure in the soil, and in the soil to the this excess pore water pressure always try to dissipate through the pores, and due to the dissipation of excess pore water pressure, the effective stress of the soil is increased, and by increase of excessive stress, shear strength of the soil also increase. And through this technique, we indirectly or directly increase the shear strength or reduce the settlement of the ground. So it is said that preloading is one of the common used ground improvement methods in practice for saturated fine grained soil. We know that pre-consolidation or consolidation method only used for the saturated soil, and it is also used for fine grained soil. So, and to generate the consolidation, we apply some loads on it because due to this load, excess pore pressure is generated. Then it is said that the basic concept of this technology is to reduce the air voids ratio, that is compressibility of the geomaterial through the concentration. It is dissipation of the excess pore pressure by applying loads on the ground surface for a certain time period and then remove it for the construction for a permanent structure. So we already discussed about the consideration. We apply load due to this applied load. First, this load is transferred to the water. Water takes the full load. Due to this load, excess pore pressure is developed, and water always try to uh, stable or try to neutral in a state, try to stable or we can say it, always try to dissipate this excess pore pressure uh, due to for stable condition. So it is dissipated through some uh, voids or through some pore paste, and due to this dissipation of excess pore pressure, effective stress increase, and by that way, settlement is creating and increase the ground strength. And it is also said that when the natural rate of consolidation is very slow, it becomes necessary to accelerate the consolidation by some means to carry out the intended activities. So we discuss this last point in the upcoming slide. That means the another means to accelerate this consolidation in this pre-consolidation technique is one of which vertical drain we apply along with the preloading. We know that due to the vertical drain and vertical drain are always made with some good porous material. So due to this vertical drain, the water can easily dissipate it and the consolidation process is accelerated and the time taken for this consolidation is reduced. So in the next slide, it is given one example that an environment designed to carry certain traffic loads. In the design, it is essential that most of the settlement has taken place before the pavement is constructed to avoid the excessive cracking on the road. So, this pre-consideration is mostly used for the road construction. So, to make the embankment. So here one diagram is shown that when we construct some structure, this type of soil, which is very soft and saturated, and we try to increase this uh, or improve this soil, we apply the preloading. And always remember the preloading or preload should be greater than the structural load which is going to build in this soil. So due to this preload, the excess pore pressure generated and consolidation happening and settlement takes place. Due to this settlement, uh, the ground is stabilized or improved. So after that, when we apply the our permanent structure on to this soil, ground is resist the settlements occurring due to this permanent because we already apply our preloads greater than the structural load and by that the settlement also we greater than our structural settlement. So by this way, we can reduce further damage of the structure or occurring due to the settlement on this ground. And if we not apply the preloads, so you can see that in this graph that when we apply the preloads, the ground is settlement. The ground settlement is like that. But after few times, and we can say that our targeted settlement for the permanent structure is up to that much. If you see in the slide, I draw some horizontal line up to that. Huh? And we apply the preloads greater than this settlement because we need to take care of up to this much. So we always apply preload for the time being when the settlement is greater than our actual needs. And after that we remove our payloads. So due to the removal of this load, soil try to regain its strength or try to rebound its position. So there are some rebound nature of soil due to the unloading of the payload. Okay, and after that, when we apply our structure, permanent structure on this soil, the ground is resist to settle this permanent structure below the our preload settlement because our preload is greater than the structural load. So also corresponding settlement also greater than our structural load. If we do not apply these preloads, ground settlement is like that. So by this way or by this technique or by this consolidation technique, which is applied before the construction of the permanent structure, we can reduce the settlement of the ground and also we can increase our strength of this soft soil. So by that methodology, we use in pre-consideration technique. So in the next coming slide, it is about discuss about the implementation. So it is said there the rate of consolidation is proportional to the square length of the drainage path. If you remember in the basic soil mechanics or geotechnical engineering, we studied about the only consolidation method which is given by Tarjani. And where we come some constant which is the time factor is equal to the coefficient of consolidation into time divided by the length of the drainage path. So square of the length of the drainage path. So if the time factor is constant, it is a one of constant for particular soil. So by this equation, we see that coefficient of consolidation is proportional to the square of the drainage path. So the first point is justified there. The rate of consolidation, which is nothing but the coefficient of consolidation, is proportional to the square length of the drainage path. In the second point, it is said that the rate can be increased if the vertical as well as horizontal drainage paths are made available to the pore water. It is true because if you increase the D, that means D means drainage path. If we increase our drainage path, the rate of consolidation also increase. But in normal cases, we see that if it is the ground, if you see my screen, I am drawing. Uh, if it is one of the ground and we apply the preloads here, that so water try to dissipate only in the vertical direction because in the lateral direction the soil is confined. So always water is try to in vertical direction. But by some means, that means we if we apply vertical drains with some good with some wait with some good porous material like that like clean sand or gravel, if we create some vertical drain, the soil, the water is try to dissipate by this direction, also by this direction, that means horizontal direction, also by vertical direction. So if we apply vertical drains, the drainage length of the soil is increased, so automatically the rate of consolidation will increase. If rate of consolidation is increased, the time taken due to for the consolidation reduce, and the construction period also reduce. So in the third point, it is said that we already discussed that this rate of consolidation increased by this vertical drain, and this is essential a system of vertical borehole put down through the layers and then backfill with a porous material. We already discussed that some by means we can create some vertical drains, and this vertical drain should be backfilled with some porous material like some clean sand or gravel material which is good for drainage of water. And this method is first discovered or first used in California by Porter in 1936. So for very long period, this method is used to improve the ground for the cohesive soil, because we know that cohesive soil is very soft. Cohesive soil is very difficult to handle. It is very soft. You can not resist any loads. It cannot resist any loads on it. So to improve this soil, we use or maximum we use this technique, which is pre-consolidation. So here two figures is shown, that one is for when the vertical drain is reached up to a certain rock surface, and second figure is shown when the vertical drain reach through between in between some impervious layer. So you remember that if there is any hard stratum is present, the vertical drain should be reached up to that hard stratum. If there is present any impermeable layer is present in between any permeable layer, the vertical drain should be cross this impermeable layer, and up to that the drainage is happening. So you remember that if we apply the vertical drain for impermeable layer, the vertical drain should be cross or greater than the impermeable layer. In the next slide, we discuss about some basic guidelines about this uh, pre-consolidation technique and about this vertical drains. So it is said that the diameter of this vertical drain should be range in between the 300 mm to 600 mm, and it should not be less than the 300 mm, because due to this if it is less than 300 mm, it is difficult to install because the soil is considerably removed. It's not considerably removed, because if we apply less than 300 mm, the resistance of the soil to take this vertical drain is not possible. So we apply these vertical drains in between. Diameter of this vertical should be in between 300 mm to 600 mm, and also the spacing of this vertical drain should be in between 1.5 meter to 4.5 meter. And also remember that the spacing of the vertical drain should be less than the thickness of the consolidating layer, which means if we apply the pre-consolidation technique in this ground, and we need to address or we need to improve some compressible layer up to that much of height, saying h. Uh, that means the compressive layer thickness is h, and then the spacing of this sand drains, that means here here one sand drain, here one sand drain. The spacing of the sand drain should which is here given is a, should be less than h. That means a is less than h. If it is less than is, then only the drainage is happening through this vertical drain, and it is effective for this vertical drain to dissipate the excess water pressure. Coming to the next point, it is said about the grid pattern. Like other ground report technique like deep compaction or we can say repeat compaction, here we also use some pattern like square pattern and triangular pattern, which is popular. And same specification techniques or same spacing technique is used here also. That means the spacing should be for square pattern, the equivalent radius or you can say spacing should be 1.128 of equivalent radius. So we discuss it later. So it is said that the sand grains are laid out in either square or triangular pattern. For triangular pattern, this should be an equilateral triangle. That means the both the all the sides of the triangle should be equal. We already discussed in this techniques or patterns in previous techniques. Here also same case. So in these two figures, it is shown that one is square pattern and another one is triangular pattern. The triangular pattern should be maintained as equilateral triangle. So that means all the sides are equal. So coming to the next point, which is regarding the depth of the drains, and the depth of the drains should be depend on the type of the soil or subsoil. We can say that means how much depth of our compressible layer. That means if or we can say up to what depth we need to address this compressible layer. If it is 10 meter, then our drainage depth also 10 meter. But it is one good thing about this sand drain is that it can be used up to 45 meter. That means we install a sand drain up to a, or we can say vertical drain up to 45 meter, which is good for this technique because most of the ground improvement technique is limited to 20 meter or 10 meter or we can say 6 meter. But this vertical drain for consolidation, we can use up to 45 meter. That means for a huge depth, we can use this technique. So in the next point, we the type of sand we use. So it is said that clean sand or which is available readily available sand which is carry away water very quickly, we can use for this type of sand drain. And also we need to address that during this drainage the fine particle of the soil not waste out. That means it should remain in contact with this sand drain. So this type of porous material is used in our vertical drain technique. So in the next point, regarding said regarding about the drainage blanket. So if you see our previous figures, that means this figure, we, we apply the pre-consolidation technique along with the vertical drain. So there in in pre-consolidation technique, we apply some loads, which is called preloads. So in between the vertical drains and preloads, there's some small layer is constructed to drainage out the water in lateral direction. This small layer is called the drainage blanket. And this small layer it should be in between, thickness of this small layer should be in between 0.33 meter to 1 meter. And this to create this small layer, we use some good gravel material or some porous sand material. So in between the junction in the junction between the preloads and the vertical drains, we apply this drainage blanket. So it is said that after the drainage are installed, a blanket of gravel and sand from 0.33 meter to 1 meter thickness is spread over the entire area to provide the lateral drainage at the base of the field. So same. thing is told here that at the junction of the preloads, we apply this drainage blanket. So then in the next slide, here we see some figure about the surcharge or overfill. Overfill we use when we need to increase our consolidation rate more, furthermore. That means we use some preloads to induce uh, some consolidation in this soil. After further we increase the consolidation rate, we install some vertical dam. Again, further if we increase this rate, we use some extra load on it to increase our or accelerate our consolidation technique. But one piezometer used indicate the consolidation, and when this consolidation is becomes slow, the structure is smooth. This point should be remembered. That means we apply the structure rule to increase the consolidation, and we remove it when the rate of consolidation is becomes slow down. In the next slide, it is regarding about the application of the vertical load or preloading technique. So it is said that it is mostly used in the highways, airports, land reclamation, storage tanks, and buildings. And the advantages are for this technique is that preloads is a reliable ground improvement method and has a long track record. And it is often cost effective if the fill material is readily available or a part of a permanent structure. Field preloading can be easily implemented on an open net with a limited or no demand for specialty construction equipment, skilled worker, and quality assurance. So we know that in preloading technique we need only some load which is readily available for the construction in terms of the permanent instance as a part of the permanent structure or as some local fill material which is like some sandbags which is we can use some sandbags to for this to use preload like that. And if we apply only preloads on the ground, there is no skill level is used to for this pre-consolidation method. But if we apply further to increase this ground to vertical range, apply instead of vertical range, so there are some equipments or skill level is used. We can see in the next slide. In limitation, it is said that the main limitation of the preloads is longer required time for the consolidation and specially used for low permeable geometry. So we know that consolidation techniques require some times because it is very slow processing technique. Water if and also it is applied in low permeable ground geometry, which is not good for the drainage of the water. So it is take some good amount of time. So it this technique for this is one of the limitation of this technique. Also, if we apply the vertical dam, we already discussed it this point. Then, if we apply the vertical dam, there required the high head space and also require some skill level to install this vertical dam. And also to apply this technique, the area should be free from the constraint because the materials transpiration and induced ground movement, the area need to be free or for constraint from constraint. So these are the limitation of this technique. Coming to the next slide, we discuss about the strain effect and the consolidation theory. We know that strain effect is nothing but the elastic stress strain technique we apply in this here also. So it is said that although there is a lateral drainage, the lateral drainage means when we apply the vertical drainage in the horizontal direction, the water is come to this vertical drain, and after this the vertical drain is collect the water and try to dissipate this excess water. So when we apply this vertical drain, there should be a lateral drainage. Due to this lateral drainage, there are some lateral strain also generated. But when we calculated our settlement due to this consolidation, we neglect this lateral strain effect. So we simply apply the only consolidation technique, and we can we can come some formula, that is settlement is equal to mv into dp into 2h. So by this formula we can find out the settlement due to this consolidation technique. So where dp is the increase effective stress due to this uh, apply of the preloads, and h is the thickness of the consolidation layer. mv is the sorry mv is one of the consolidation parameter. Okay, so we here one formula is given regarding the three-dimensional consolidation theory. So here one partial differential equation is generated regarding this three-dimensional consolidation. So where we apply the radial consolidation, also apply the vertical consolidation. If we apply, if we not apply the vertical drains, then this CH term should be neglected. If we apply both vertical drain and radial drain, or we can say horizontal drain, then we apply both CH and CB. So it is nothing but that dou U by dou T is equal to CH into dou square U by dou R square plus 1 by R into dou U by dou R plus CB into dou square U by dou Z square. Z represent the vertical direction and R represent the radial direction. So by this formula, we can derive the consolidation time, also derive the rate of consolidation, and also derive the degree of consolidation. So in the next slide, we discuss about the equivalent radius. If you see the square pattern and triangular pattern, you can see here that each of the drains have some influence area. So for square pattern, the influence area should be half of the spacing of each of the drains. So the influence area should be like this. And for triangular pattern, the influence area should be like that. That is hexagonal shape. So if we replace this square with one circle, and we come to some radius, and this radius is nothing but called the equivalent. And also same case for the triangular also. If we replace this hexagonal to some equivalent circle, and we find the radius of this circle, it is nothing but the equivalent radius. So we here we find out one by one the radius of the equivalent radius for this pattern. For square pattern, it is uh, it is find out that for square pattern it is equal to the equivalent radius is equal to the 0.564 into spacing. Here he is here spacing. So we already discussed this type of calculation in the previous ground improvement technique, where we applied the square and triangular pattern for sand drain, sorry, for stone column, also for the deep dynamic compaction when we discuss about the pattern. So the equivalent radius here is equal to the 0.564 into spacing. For triangular pattern, it is equal to the 0.525 into spacing. And we also know that the area for this equivalent area of this equivalent circle for triangular pattern is equal to the 0.865 into square of the spacing. So by this formula we easily find out the equivalent radius. Coming to the lecture 2 of this module 7, that means we discuss about the different consideration, rate of consideration for different, that means for radial direction and for the uh, vertical direction. So to find out the rate of consideration for the radial direction, one scientist that is name is Baron, he gives one curve for to find out the degree of consolidation for in radial direction based on the uh, in between the degree of consolidation for radial direction in terms of this time factor. This means TR. The TR is nothing but the CH into T divided by small t divided by 4R square. That means TR is time factor and CH is the coefficient of consolidation in radial direction. T is the time period in AR or so in month. There is one influence area, or we can say equivalent radius. Up to that, this sand rain is effective for this region. And if we consider the R is the radius of this equivalent circle, and so for horizontal or you can say radial drainage, the drainage path should be diameter of this circle. That means nothing but the 2R. So if we know that the time for the time calculation of the time factor, there is use drainage square of the drainage path. So if we square the this diameter, we can come to this point that 4R square. So by this way, we can find out the time factor for the radial drainage. So after finding the time factor for the radial drainage, we find out the n, which is a constant. So to find out the n, which is very simple, uh, which is nothing but the ratio of the diameter of the influence equivalent circle divided by the diameter of the sand ring. So by this way, we find out the uh, one parameter which is n, and by this way for each of these n we construct the this curve uh, which is range for n is equal to 5 to 100, and by this curve we easily find out the degree of contribution for this parameter. Now we find out the vertical drainage or vertical consolidation, degree of consolidation. To find out the vertical degree of consolidation, we use to first find out the time factor for the vertical name, this which is nothing but CV into T into H square. So by this way, we find out the time factor. After that, we need to find out the excess pore pressure at the top of the surface, also at the bottom of the surface. If we find out this excess pore pressure is uniform throughout this compressible layer, then one another parameter is used m, which is equal to 1 for when the excess pore pressure is uniform throughout the layer. So m is nothing but is equal to the u1 by u2. So here we see the different case, and for this different case, different m is calculated. So for first case, when u layer uh, excess pore pressure is uniform throughout this layer, then the m is equal to 1. And when the excess pore pressure is 0 at the top layer and there is some value present at the bottom layer, then this m is equal to 0 because m is equal to u1 by u. And like this, to a different case, we come to different number of cases. And for this different m, different number of curve is represented here for this consultation. And by this way, we find out the uh, degree of consideration for different time factor, which is required for our construction time period. So now here one some point made regarding this horizontal, or you can say radial consolidation, also for the vertical drill. So first we need to find out the time factor, and for time factor we need to find out the coefficient of consolidation. Also need the time for this construction or consolidation time period, and also need to find out the drainage part. After that, this formula is used for this vertical drainage. For radial drainage, we use the Barron's curve, which is already discussed regarding this. And after finding the vertical consolidation, degree of consolidation, and degree of consolidation, we find out the total consolidation. To find out the total consolidation, we combine this vertical as well as radial consolidation, degree of consolidation. So one formula is used to find out the combined degree of consolidation, which is equal to 100 minus 1 by 100 into 100 minus vertical consolidation, degree of consolidation into 100 minus radial degree of consolidation. So by this formula, we can find out the combined effect of the degree of consolidation. So here one problem is given regarding uh, these formulas, and which is a trial and error based problem. We need to find out in this problem. We need to find out the diameter of the vertical drain. Also find out the spacing, effective spacing of this vertical drain. So now we try to solve this problem. So it is said that a soft clay layer MV is equal to 2.5 into 10 to the power 4 m square by kilonewton meter square per kilonewton. CV is equal to the 0.187 meter square per month is 9.2 meter thick and overlies Empire pervious sheet. An embankment to be constructed in 6 months will subjected the center of the layer to pressure increase of 100 kN per meter square. It is expected that a roadway will be placed on the top of the embankment 1 year after the start of the construction, and the maximum allowable settlement after this is to be 25 mm. Determine the suitable sand drains system to achieve the requirement. We can say this is type of problem is regarding as the design problem. We're designing the vertical drain diameter and also the uh, spacing of this vertical drain. So first we need to find out the total settlement due to this preload, total settlement of the soil regarding the lifetime of this construction. To find out the total settlement, we need the formula is MV settlement is equal to MV into DP into 2H. So 2H is nothing but the height of the thickness of the compressible layer. So MB is here given is 2.5 into 10 to the power minus 4, and BP, that is increased stress pressure, is given here is 100 kilonewton per meter, and thickness of the layer is given is here is 9.2 meter. So after uh, put all the values, and we find out the total settlement of this kind of ground is equal to the 230 mm. But here is one condition is given here, that the maximum allowable settlement should not be greater than 25 mm. That means up from 230 mm, we uh, settle our ground up to 230 minus 225 mm. That means up to 230 minus 25 mm, that means 205 mm. Up to that much we can improve our ground. That means if we improve our ground up to that much, the structure which is built after the pre-consideration, it can take or it can allow up to 25 mm. So it means safe for this soil. So by this way, we find out the degree of consolidation. We know that degree of consolidation is equal to the settlement during this pre-consolidation and settlement, maximum settlement for this ground. So for by this way we can find out the degree of consolidation, or it is come to 90%. So now we come to our design problem. We're designing our sand diameter and spacing also. So first we calculate the time period for this embankment. So we said that the complete construction of the embankment is done is in between 6 months. That means from 0 month the load is here is 0. After that 1 month there is some load. After like that, in 6 months the complete load is put on this ground in the embankment shape. So we average the time period for is, that means 0 plus 6 divided by 2. So we come that 3 months. So that means we convert this load into uniform time. That means in 3 months the load is applied for this consolidation technique, and we need to find out uh, this consolidation for 1 year. So remaining 6 months also add with these 3 months, and the total time is come out is 9 months. So so it is said that we assume the settlement is commenced at the half of the constructive time, that means 6 divided by 2, and the time reached to for this 90% degree of consolidation is equal to the 9 months. So after that we find out the time factor for the vertical technique. So it is nothing but the CV into T divided by H square. H is the thickness of the compressible layer. Remember, if the if there is there is impermeable, if the compressive drainage of the compressive happening in the one direction, then total the drainage path should be total thickness of the compressible layer. But if the drainage is happening in the both the direction, that means at the top also at the bottom, then the drainage path should be reduced, and it is come to h by 2. You should remember. But in our case, it is said that it is overlies at the impervious sea. That means the drainage is happening, or we can say vertical drainage is happening in only one direction, that is in upward direction. So we here we use only the H not h by 2. So by this way, we can find out the time factor for vertical drilling. After that, for this time factor, we come to the charts which we can discuss previous this chart. And for this time factor, we find out the degree of consolidation for the vertical line by these charts. And we come to that for vertical drain, the degree of consolidation is 16%, but our targeted degree of consolidation is 90%. So by these preloads, we need to come to not come to this 90% because the vertical drain is only vertical consolidation only take up to 16%. So we need to install vertical sand drains in this soil. So now we apply trial and error method to find out the diameter and spacing of this sand drain. So first we try with 450 mm diameter of sand drain. So and also select n. N is equal to the ratio of the inflow area of this sand drain divided by the radius of the sand drain. So we select the diameter of the sand drain is equal to 450 mm and n is equal to the 10. So by this way we find out the radius of influence of this water sand rain. After this we apply here the triangular pattern. So we know that the radius of influence is equal to for triangular pattern is equal to the 0.525 into spacing of the triangular pattern. So by this way, we can find out the spacing of this triangular pattern, which is come to a 4.3 meter. After that, we find out now we know that if we reduce the our radius of influence, or sorry, if we reduce our spacing, the vertical then is more effective. That means it is the consolidation of the vertical lane is increased. So we reduce our spacing and we can select that 3 meter for spacing for this triangular pattern. And now we can again find out the R for this triangular pattern. After that we find out the N, one parameter, which is nothing but the radius of influence divided by the radius of the sand grain. And we find out 7, N is 7. And then we calculated the time factor for in radial direction by this formula, that is CV into T divided by 4R square. And we come to that time factor is equal to 0.169. After all these parameter, we can find out the degree of consolidation in radial direction by Baron charts, and it is come that a radial direction degree of consolidation is equal to the 66% from this chart, and we applied the combined consolidation formula. After that, we find out that the combined consolidation is equal to 71.4%, which is not sufficient because we need to take care 90% of degree of consolidation. But for 3 meter spacing, the degree of consolidation, combined degree of consolidation is about the 71.4%. And to increase to improve our ground up to 90% degree of consolidation, we now reduce our spacing, and from 3 meter we use 2.25 meter. For 2.25 meter the radius of influence also change and also change. After that Again, we calculated the time factor for this radial consolidation, and from this chart again we find out the radial consolidation degree of consolidation, which is come to the 90%, and then we find out the combined effect of this degree of consolidation for vertical drainage and for the radial drainage, and we see that it is come about 91.6%, which is more than the our desired degree of consolidation. That means our construction is safe when we apply the spacing is equal to 2.25 meter. So by this way, by this trial and error method, we can find out the radius of the sand grain and also find out the thickness. Find out the spacing of the sand grain. And like this way, we design the vertical sand drain. So now we take breaks for few minutes. After that, we discuss another vertical drain, which is called prefabricated vertical drain. So after this break, I am discussing regarding this. Now we will take break for few minutes. I will join in 5 minutes. Please stay on the line, and we can again re continue from our lecture from this. So now we take 5 minutes break. Don't leave the meeting. Again, welcome to this session. Now we try to complete our further lectures regarding these pre-consideration methods. So we already discussed about the what is pre-consideration and what is after that we discuss about the what is the use of the vertical range in the pre-consideration. Now we discuss about the another vertical range. Uh, uh, we discussed already about the sand range. Now we discuss another type of vertical range which is used during the pre-consideration, which is called the PVT. PVT is called the prefabricated vertical range. So it is said that the prefabricated vertical range is generally a strip about 100 to 120 mm wide and 5 to 10 mm thick. And for the analysis, this converted into the equivalent circular drain. That means all the if you see our three-dimensional consolidation theory, all the calculation regarding that consolidation is in terms of circular drain. So if we apply the prefigured vertical drain, we for calculation of the consolidation theory or consolidation, we need to convert this prefigured vertical drain. If you see in our pictures here is it is one of the prefigured vertical drain. So it need to convert it into the equivalent radius of the or equivalent circle of circular drain or equivalent radius of the circular drain because our all the concept theory is regarding for the circular drain. So after uh, converting, there is for converting there is two method is applied. One is to equate the equals area cross section area of both equivalent circle or for this strip prefigured vertical drain, or either another way is to equate the perimeter of these two. One is prefigured vertical drain and another say equivalent circle drain. So most of the case we use the second one. That means we equate the perimeter. We equate the sorry. There is two part. We equate the perimeter of this both drain. So this formula is arrived after equating the perimeter. That means for circular drain, the perimeter is pi d. Here, the diameter of the drain is taken is dw, and we know that the area perimeter for rectangular is 2 into a plus b. By this formula, we find out the equivalent diameter for the circular drain, which is converted uh, when the strip is converted to the circular drain. So here we also same for this PVD we can also use the square pattern and also for the triangular pattern. And same for this we find out the equivalent influence area for each of these PVD. That means PVD vertical rings. So after we converted this square pattern into the some equivalent circle, so find out the same. The radius diameter for this square pattern is equal to the which is already calculated in previous that 1.128 into s. S is here spacing of the this spacing in between the drains. So for square pattern, it is find out that the influence diameter is equal to the influence circle diameter is equal to the 1.128 into spacing. And for triangular pattern, it is find out the 1.05 into spacing. If you remember that for sand ring, we find out the equivalent radius is equal to the point for square pattern point 5 to 5 for sorry for triangular pattern it is point 5 to 5 into a. If we multiply into 2 which is we come to that value. Same for square pattern also. If we multiply 0.564 into 2 we come to that point. So by this way we find out the equivalent diameter for each of the equivalent influence area diameter for each of the drains. So come to the next slide. Here is also given one chart regarding the degree of find out the degree of consideration based on the time factor, different time factor. And here also use one parameter n, which is previously also used in sand drain also. So n is varying from 5 to 100 here. Previously I said 5 to 100. N is varying from 5 to 100. And n is defined here is ratio of the diameter of influence area and also divided by the ratio, diameter of the uh, equivalent diameter of the PVT. So by this graph, we easily find out the degree of consolidation for radial direction and also for in vertical direction. For vertical direction, we use only the dashed chart or dashed line to find out the vertical consolidation. For radial consolidation, we use for this charts this line also this line based on the different angle. Here horizontal flow is nothing but the radial flow because in plane if you see in plane view the radial flow and horizontal flow is almost similar. So this curve is used for both the case like that. If we in cross sectional view like that, the drainage is like that. Coming to the next slide, we discuss about the different consolidation formula based on the vertical drainage. So if this formula is also you can also see in the basic soil mechanics also you can find out this formula which is based on 1D problem, 1D consolidation. So for 1D consolidation, we and for vertical drain also, vertical consolidation, we use this formula. If the degree of consolidation is less than 60%, we use this formula, that is PV. P is here, time factor is equal to pi by 4 into U by 100 square. If the degree of consolidation is greater than 60%, PV is equal to 1.781 minus 0.933 log 10 100 minus C. And for any case, sorry, uh, for for any case, that means for any value of degree of consolidation, we can apply this formula, this big formula. So no need to consider the degree of consolidation less than 60% or greater than 60%. So we directly use this formula. But this formula is used for the vertical consolidation only. For here is one chart is given for vertical consolidation, which is based on this formula. Same is which is previously find out. So now for radial drainage, we apply some empirical formula to find out the degree of concentration. So for which is based on the time factor of for radial drainage. So here it is given that if degree of concentration for radial drainage is equal to the 1 minus exponential to the power e to the power minus 8 tr. Tr is here time factor divided by fn. Here Fn is one parameter which is find out about the n square divided by n square minus 2 into ln into ln log n minus 3n square minus 1 divided by 4n square, which is almost equal to the log n minus 0.75. So by this formula we find out the Fn. After finding out Fn and Tr, we find out the degree of consideration for radial direction. So if we consider the wall resistance of the prefabricated vertical beam, then this formula is modified because in previous case we neglected the wall resistance. So if we consider the wall resistance, the extra term is come is here is pi z into 2l minus z kh by qw, where L is the longest drainage path along the vertical drain, Z is the depth, Q is the discharge capacity of the prefabricated vertical drain. So we modified our formula like that. So if this formula is used for when we apply, assume there is wall resistance in between the vertical drain, prefabricated vertical drain. But if the discharge in between the prefabricated vertical drain is more in a large, then this part is neglected and we consider the previous one only. That means ln in minus 0.75. So this next slide it is discussed that it can be seen that the equation that when QW, that means discharge, is sufficiently large, the last term is in this equation will be very small, and so that the effective of well resistance can be ignored. Some modern high quality PFBD vertical drain products can be sufficiently large QW. Therefore, well resistance may be ignored in the design when the PVD with sufficiently large value of QW. And particularly this requires uh, QW value of the PVD to specially checked as a part of the quality control process regarding the construction or during the construction. That means in if we apply the large QW, that means if we apply PWD which carries the large quantity of QW, this is discharge, then we automatically neglect the oil resistance. But in case our discharge in between the uh, discharge in between the sorry, our discharge in between the preferred vertical drain is reduced, then we need to consider the oil resistance of in this formula. So in the next slide, here we discuss some methods to find out the degree of consolidation in the real field. When we not we need to know, or when the time is required for the consolidation is not known to us. So for that, we three techniques is used to find out this degree of consolidation, and also to find out the consolidation time period. So in first, we consider the radial degree of consolidation is equal to the total degree of consolidation, or our achieved goal. Uh, So after that, we find out the time, and also find out the TR and UR, and ignore, in this case we ignore the vertical tail. And by this trial and method, we find out the T, that is time, for this degree of consolidation, uh, a time period for this consolidation. After that, we find out the vertical consolidation, and after finding vertical drain and also finding the radial degree of consolidation, we combinedly find out the total degree of consolidation. If the total degree of consolidation is smaller, or we can say is greater than our considered degree of consolidation, so we need to calculate constructed our program again. So by this iterative way, we can find out or we can say by this trial and error method, we can find out our total degree of consolidation, and also find out the uh, total time period required for this consolidation technique. So now we come to discuss the smear effect, or smear regarding this installation of the vertical day. So when we apply, or when we install this vertical drain into the ground, the surrounding soil of this vertical drain get disturbed. Due to this disturbance, the particle structure of this vertical drain around this soil around this vertical drain is change. Due to the change of this particle structure, consolidation coefficient of consolidation, and also the coefficient of permeability of this surrounding soil is reduced. And due to this reduction, degree of consolidation of this soil also reduced. So we need to take care this smear effect in our calculation also. But in previously discussed formula, we need to know and not take care of about the smear effect. But now, if we consider there is a disturbance around this, sufficient disturbance around this uh, vertical drain, we need to consider the smearing effect. Smearing effect is nothing but the disturbance of surrounding the vertical drain. Regarding this, the permeability is reduced, coefficient of consolidation also reduced. So here is one guidelines is given that the diameter of the smearing zone is equal to the 4 to 7 times of the diameter of the uh, sand drain. We can say diameter of the PVD drain. So if the smearing, so by this we consider the influence of the smearing zone around the, or find out the influence of the smearing zone around the these vertical drains. So in the next slide, we modify our formula when we consider the smearing effect. So here little adjustment is applied regarding this smearing effect. So the Fn is changed once some extra term is used, which is ln s into kh by ks minus 1, where s is equal to the ratio of the diameter of the smearing zone uh, to the diameter of the vertical ring, and this range is in between the 4 to 7 times, in between 4 to 7, and k is here the coefficient of permeability or permeability coefficient in horizontal direction while there is no smearing effect, and ks is the coefficient of permeability when there is smearing. We need to consider the smearing effect. So by this way we modified our formula and find out the radial degree of consideration when we consider the smearing effect. Now we try to solve few problems regarding this consideration formula. The first case regarding this PVDs. The first case we consider the without smearing effect. So here it is given the thickness of layer is given 10 meter, and which also is laid on some impervious layer, and spacing is given is 2 meter. PVD is dimension is given 100 mm and 4 mm, and coefficient of consolidation in vertical and horizontal direction is given, permeability is given is uh, 2 meter square and 3 meter square, and boundary below the sorry, and now we calculated the degree of consolidation achieved in 1 year times. So it is very simple problem. First, we find out the radius of diameter of the influence area for each vertical ring. So we find spacing is given, and we here it is given the square pattern is applied. So formula is 1 point d is equal to the 1.128 into s. By this formula, we find out the diameter of the influence zone, and after the dimension of the strip, or we can say PVT is given, and it is converted into equivalent vertical ring. And so it is find out that we apply this formula 2 into a plus b by pi. By this formula we find out the diameter of the vertical ring, which is come to the 66 mm. After that we find out one parameter, which is n, which is nothing but dE by dW, and it is come to this 34. After that, we find out the Fn for no smearing effect. That means we do not consider the smearing effect. So it is nothing but ln in minus ln log n minus 0.75, and it is come to 2.75. And then we find out the time factor for radial drainage, and it is come to uh, 0.589. And after that all the values if we put in this formula, that is for find out the radial degree of consideration, we find out about that the radial consideration is about 81 point, we can say almost 82%. Now we find out the degree of consideration for vertical vertical direction. So for that we need to find out the time factor for vertical direction, and the drainage path for vertical direction is about 10, and by this formula you can find out easily find out the uh, degree of concentration in vertical direction, and it is come about 16%. After that we combine degree of concentration find out, and it is about 85%. Now the same formula is used for the smearing zone, and there is present smearing zone, and it is given that for smearing zone, the smearing ratio, which is nothing but S, is equal to the ds by dw is given here is 3, and coefficient of permeability for smearing zone is given is here is 1.5 meter square. That is which is previously given. Here it is 3 meter square per year, but here it is given is 1 per meter. That means for due to the smearing effect, the coefficient of permeability is reduced. But due to this reduction, we find out the uh, due to this smearing effect, this coefficient of permeability is reduced, and we need to change our FN formula. Now, all the values which we find previously up to vertical consolidation is same. We need to change our formula for the radial direction. For radial direction, we need to change our FN. By this formula, we need to modify our FN, and it is come about 3.88, and KR by KS is here. KR is 3, KS is here 1.5, and we find out it is 2. So, and we find out UR is equal to about 70%. And if we see that when we consider consider without smearing effect, this value is come about 80% or 82%. But after smearing effect, the degree of concentration is reduced because of the reduction of the permeability or coefficient of consolidation. So it is come about the 70%. And also the combined effect of the degree of concentration also reduced, which is previously find out 85%, or here it is find out 75%. So you clearly see that the smearing zone, the effect of smearing, when you consider the degree of concentration is reduced. So by this two formula, we can easily find out or we compare the effect of smearing zone. What is the effect of smearing zone? Now coming to the next slide, we discuss about the designing step of the or some points about the design of the this PVD or vertical ring. So first we need to check the stability of this PVD. For stability or during the stability or immediately or during after filling the sand, we need to check the stability of the drill, and this can be achieved by formulating the degree of consolidation. That means after each of the installment or layer, we need to find out the degree of consolidation, and for this degree of consolidation, this drain is stable or not, we find out. And for each step, we need to find out the stability. Each step means we that is here if we apply the vertical drains here, and above that we apply preloads. We not directly apply all the preloads at once. We step by step we apply this preload. That means first layer wise layer we apply this preload. The first layer, if first we apply some amount of preloads or some percentage of total preloads, and we check the degree of concentration regarding this preload, and we try to dissipate or give some time to dissipate some water and stable the ground. And then after that we increase the preload further in the next step, and again we give some time and to dissipate the excess pore water pressure and stabilize the ground. By the step by step method, we increase by the step by step method we increase the total degree of increase achieve the total preloads, and after that we achieve the total degree of consolidation of our construction. It is applied because if we apply the total preloads at once, the ground may be collapsed because the consolidation technique, most of the consolidation method is applied for the soft soil, and we know that soft soil is not good for the bearing capacity, bearing. So the ground may be collapsed due to the sudden apply of the preload or total amount of preload apply of the total amount of preload at once. So we apply this preload step by step, and we need to check the stability for that. That means we need to check whether this for this load, the ground is carry this load or not. We need to check for each step. Then we need to check the settlement criteria. That means after each of the preload or drain, we need to find out the total settlement for this preload. So we need to also check during our design step, designing. Then we need to check the cost of the construction. So if the time schedule is not very tight, a cost analysis can be used to investigate whether in the event of no vertical drainage being used or whether it is used or not, an early investment in the sand structure and annual loss of the interest during a number of years compensate for the cost of vertical drain system. That means if the construction cost is not that means if our construction cost is or we can say our time is not very tight. That means the time required for the construction uh, um, is not our main goal. Then we only apply the preloads to generate the consideration. But if we need time is the major constant if in our construction if the time is the major constant in your construction, that means we need to perform our construction in very quickly, then we apply the vertical drain and also calculate the whether this vertical drain is cost effective or not. That means the total cost of construction is not exceeding when we apply this vertical drain. We need to check this type of consideration and also have to check the malfunctioning of the vertical drain. That means whether the vertical drain is functionable or not, whether it is draining the water from the ground or not. We need to check in between our construction. And here also one point is given that actual design of a vertical drainage system covered working out which type of drain to use, including the diameter, width, drainage length, and relative drainage spacing. And the choice of the drain length is often governed not only by the thickness of the strongly compressible layer but also by the consideration of the geohydrological or environmental nature. So this type of consideration need to be taken during the installation of the PVD. That means the spacing, diameter, drainage length, and drainage spacing we need to consider during our apply the vertical drain for the pre-consideration. Now here we discuss now here discuss given some different types of prefigurated vertical drain. Figure is given. So here three types of prefigurated vertical drain figure is given. One type is like that, another is one like that, and last one is like that. And here also shown some figure to installation of the prefigurated vertical drain. And it is a by static push method this prefigurated vertical drain is applied. So by the static sorry for that. By the static push method, this prefabricated vertical drain installed into the ground, and this figure is shown like that. You can see that one rod like structure is installed or driven into the ground like that, and here is some opening is given to drain out the water. Like that way, we install the PVD vertical into the ground. Now, now we discuss about the construction technique of this prefabricated vertical tape. So here it is said that conduct a proper site investigation to establish the soil profile on the site, characterize the geotechnical property of the soil, and determine the design parameters. So not only for this technique and for all the techniques, ground technique, the first step is that we need to investigate the ground or site. For that, we need to find out the soil properties and we will also determine the design parameters. And after that, determine the depth the P50 vertical drain need to be installed and pattern of the installation. That means we need to find out up to what depth this P50 vertical drain is applied to consolidate out the water or drain out the water. And also decide the what type of pattern is suitable for this site, either square pattern or triangle pattern based on the accessibility of the area. Then select the preferred vertical drain that meets the design specification and design requirement. That means what is the diameter of the preferred vertical drains and how what is the length about the preferred vertical drain regarding the our design criteria. And calculated the spacing to achieve the required design spacing. That means we need to find out the effective spacing up to for which the degree of consolidation is our meet our degree of consolidation. That means we need to find out the spacing for which is effective for our goal or to meet our required or desired degree of consolidation. We need to find out. Then we estimate the ground settlement and draw the structures placement plan. That means we estimate by some Baron method or some charts to find out the vertical degree of consolidation and also find out the radial degree of consolidation. And by this, we also find out the both combined effect of degree of consolidation. After that, we find out the total settlement of the ground during this pre-consolidation. And for the what amount of load is required, we also need to find out. And then install the PVD and carry out the quality control test and inspection during the PVD installation at the predefined determined interval. That means after installation, we need to check that whether this PVD is working or not. That means it is draining the water or not. We need to check out in at regular intervals or time intervals. That means this we need to maintain this drainage in regular interval. And then design a field instrument scheme, install instrument, collect field monitoring data, and monitor the soil improvement process. That means after the applying the pre-consolidation technique, we need to check the ground improvement or ground property in regular time. After that, uh, we need to find out by this parameter whether this ground is achieve our goal or not or improve to our fit our targeted goal or not, we need to find out in the regular interval and then calculated the degree of consolidation and other design parameter used for the design and check whether the design specification have met or not. We already discussed them. That means at last we check the whether the consolidation is match our targeted consolidation work. After certain period of time at regular interval, we need to check for every drainage or for every drain vertical drain. Now we discuss about the specific soil parameter that is regarding for the design of the soil improvement. First one is we need to consider find out the pre-consolidation stress, that means sigma p. Also find out the over consolidation ratio for this field. And both this use for finding out the settlement of this uh, for this ground. And then we need to find out the coefficient of consolidation for in the both the direction, horizontal and vertical direction. And by this coefficient of consolidation, we find out the degree of consolidation. And also by this coefficient of consolidation, we find out the coefficient of permeability in both the direction, horizontal and vertical direction. After that, we also need to find out the diameter of smearing zone. That means the disturbance occurred due to the installation of the vertical drain, P-field vertical drain, error surrounding the drain. We also need to find out, and the also find out the permeability of this surrounding soil or disturbed soil, or we can say smeared soil. We need to find out. After that, we also need to find out the coefficient of compressibility, that is CC, also find out the coefficient of recompressibility, CR, and sometimes also find out the secondary compression index, this is C alpha, regarding the estimation of the settlement. And then we need to find out the undrained shear strength, that means whether the soil is take the loads or not after the improvement. We need to find out and also find out the young modulus of the soil. Like that, we all the soil parameter we need to find out it, before and after or during the construction or during the uh, this improvement technique, pre-consideration technique. Now come to quality control. So here it is said that proper quality control and assurance are important part of the preloading technology, which contribute to the successful field performance. And the material is used for this quality control is vertical drain, drainage layer, water collection pipes and connector. We need to check or all these parameters during this construction of this vertical drain. Now field monitoring and performance evaluation. That means during this uh, pre-consideration, what parameter needs to check, we need to uh, find out. And for this, what type of instrument is used here, we need to find out. First one is we need settlement plates for measurement of the embankment settlement. Extension meter points needs to find out the soil compression. Inclinometer needs to find out the soft soil horizontal movement. Piezometer needs for pore water pressure, measurement of pore water pressure of the ground. Groundwater observation well is need to check the level of the groundwater. Alignment stack is need for ground surface movement. Check the ground surface movement, and survey point needs for embankment and ground movements to check the embankment and ground movement. These are the instrument and needs during the pre-consideration. To check the pre-consideration, and then also this instrument serve some purpose also, like that to ensure the stability of the environment and also to check the performance of the preloading, and also used to determine the time for the next stage loading, and also to provide the field data to back calculate and verify the soil parameter used in the design. All this instrument is used regarding this purpose during this pre-consideration technique. And now come to the field monitoring and performance. Further, it is said that in addition to settlement, horizontal displacement rate, pore pressure, we also need to evaluate the uh, performance Vinicius stress. We need to perform Vinicius stress also to find out the strength of the soil. during the before, during, or after the preloading apply. That means by this bean shape test, we need to find out the strength of the soil uh, due to the uh, pre-consideration, and also apply the slope stability analysis to find out the soil strength regarding this slope, stabilization of the slope. And all these things are need to performance need to consider during the performance, safely performance of the pre-consideration in a soft soil. And this is all about the this is all about regarding the pre-consideration. Now we discuss the previous year assignment problem, uh, which is in the year of 2021, given in the year of 2021. After that, we concluded our session. Now we we discuss. Before that, we briefly discuss about the pre-consideration. What we discussed till now. First, we discuss the what is pre-consideration and what is used regarding this pre-consideration, which is nothing but the preludes we use for pre-consideration, and why it is used. We need to stabilize the ground and settle the ground, and increase the strength of the ground by the consideration we need to. Then we discuss the vertical drain, what is the diameter need for the vertical drain, sand drain, and also discuss about the depth of the drain we use, and spacing, square pattern, triangular pattern also discuss, and also discuss the different charts regarding the degree of consolidation, find out the degree of consolidation in radial direction also, and also find out the vertical direction after by Baron charts. After that, we will discuss about the another vertical range, which is the P50 vertical range, which is better than the sand range also, because the dimension of the this P50 vertical range is less than the uh, this sand range, but installation process is quite difficult. And but uh, the rate of consolidation is more in case of in this prefigurative vertical tone than the centric. And we're also discussing about this regarding this prefabricated vertical drain. Sorry for that. We're discussing about the regarding this prefabricated vertical drain, and uh, also discuss that. After that, we discuss the snaring effect of surrounding the this prefabricated vertical drain, and discuss the some empirical formula to find out the degree of consideration for this PVD or prefabricated vertical drain, and we solve two problems. Now we discuss the assignment problem or previous year assignment problem in our session, which also the solution also given to this Nptel website, and we discuss one by one. 10 problem is given. First problem is given that choose the correct statement for the ground movement improvement by preloading technique. First one is this option is given is preloading is especially used for the low performance geometry, which is true. Field preloading can be easily implemented in an open land with a limited resource. This is also true. And the basic concept of preloading is reduce the void ratio of the geomaterial throughout the consideration. So all the above option is correct for this problem. And second one is also said that choose the correct statement about the sand rate for use in pre-consideration technique. So first one is given there, sand rains are effective in spacing if the spacing is less than the thickness of the concerned rate. which is true. Sentences are effective if the spacing is more than not, which is not true, and equal to or is not true. The correct answer is here is option A. That is, sentences are effective if the spacing is less than the thickness of the consolidation layer. The third one, it is said that during the preloading process, core water pressure is measured by, which is measured by the which one? Piezometer. We know that piezometer is used to find out the core water pressure. So correct answer is here is option C. Fourth one is said that select the correct statement about the field monitoring and the performance evaluation in preloading method of the ground improvement. So option is given here to ensure the stability of the embankment, assess the performance of the preloading, and to verify the soil parameter used in the design. So all the above correct option is correct because we need to when we apply the field monitoring and performance evaluation technique, we will ensure the stability and also ensure the preloading performance and also verify the soil parameter used in the design. So correct option is all the above. Option D. In fifth question, it is said that choose the correct statement about the smear effect in the vertical drain. First option is given here is that during the installation of the vertical drain, the surrounding soil of the around the drain is disturbed, which is correct. Coefficient of concentration in the smear zone is reduced, it is also correct. And the coefficient of permeability in smear zone is reduced. This is also correct. The correct option here is option D. All the above. The correct answer is option D. Now, sixth question. It is said that diameter of effective vertical drain for triangular pattern. So we find out that this is option A. We know that D is equal to or DE for the effective vertical drain. DE is equal to the 1.05 into A. A is the spacing or S. We can say S is the spacing of between the vertical tape. The correct option is here is option A. Now from 7 to 7, one problem is given, which is very simple. Here it is given there, said that a soft clay layer is 10 meter thick, MV is 3 into 10 minus 4, CV is 0.18 meter square per month. Overlies an impervious state, that means drainage is happen only in one direction, vertical direction, and embankment to be construction in 6 months. The time period is given is 6 months, and will subjected the center of the layer pressure is increased due to this preloading is 100 kN per meter square. That means del P is given. Now find out the total settlement of the embankment. Similar type of problem is small in our session also. That means total settlement del E is equal to mv into del P into H. H is the thickness of the layer. So by this formula we can easily find out. So here we see that as the solution is given that mv del P into H is after putting all the value we find out that total settlement is 300 mm. So correct answer is here is option A. Now from question 8 to 10 we need to solve now one by one, which is based on one problem only. Here it is said that PVDs, that means pre-fabricated vertical drain, were installed in a compressible clay layer of 9 meter thickness of in a square pattern. That means thickness of the layer is given is H is given 9, and also the pattern is here is square with the spacing given here is 2 meter. Then pre-fabricated vertical drain dimension is given 110 mm, 5 mm thickness. Coefficient of consolidation in vertical and horizontal direction is given 2.5 meters square per year and 3.56 meter square per year respectively. And we need to find out first question, option 8, question 8 is given. Find out the degree of concentration due to the radial flow or radial drainage for 1 year. So for that, if you see in my slide, the solution is given here. For this, we need to first find out the diameter of the influence area for each of the drain. So it is said that it is square pattern. So this formula is used, that is 1.128 into S is the spacing. So first we find out the diameter of the influence area. Then we find out the time factor of the for the radial flow, and which is come at 0.707. And now we convert this uh, uh, PVD dimension into a equivalent circular drain, and we find out it here by this formula. We find out it 73.21 mm. After that, we find out the n, one parameter, which is used to find out the degree of concentration, which is the ratio, which is equal to the ratio of the influence diameter, area of the influence diameter, and the area of the sorry, uh, diameter of the influence area, and the diameter of the divided by the diameter of the sand drain, or sorry, PVD drain. So after that, we find come to the point that n is equal to the 30.28, and after that we find out Fn. Fn is equal to nothing but ln log n minus 0.75, and all the values which is find out previously we used in this formula. You can see that in our screen that 1 minus exponent e to the power minus 8 tr divided by Fn. And putting all the values in this formula, we find out the coefficient of consolidation in the radial flow, which is nothing but which is come here 88%. So the correct option here is option D, that is 88%. Now in 9 question, it is it is said that find out the degree of consolidation for the vertical flow, and for that we need to find out the time factor for the vertical flow, which is Cv into T divided by h square. H is here is 9 because only one direction, in the vertical direction the drainage is happening. So after that we find out the Tv, and after finding out the Tv, we apply this formula, that is Tv is equal to pi by 4 into uv divided by 100 whole square. So if we put all the values here, we find out the UV, that is degree of concentration in vertical direction, which is come about 20%. So the correct option for this is option C, that is 20%. Now option 10 is said that assuming the smearing ratio is 3 and the horizontal coefficient of the consolidation of the smearing soil is 1.8 meter square per year, and kh by kh, that is coefficient of consolidation and coefficient of coefficient of permeability, divided by the coefficient of permeability with smear zone is equal to 2 given, and find out the degree of consolidation in the radial zone for the smearing effect. So first we need to modify our formula, and for this we first need modify our Fn. Here is Fn is need to change, and it is given here is by this formula is that means log n minus 0.75 plus log s into KR by K is minus 1. By this formula, we find out the Fn. After that, we find out the uh, time factor for this sphere zone, radial time factor for the sphere zone, and we find out it about the 0.35, 0.353. And if we put all the values in this formula, that is UR is equal to 1 minus e to the power minus 8 TR divided by FSN, and we put all the values, we find out that the degree of consolidation is reduced and it is come about 53%. And for that, the correct option is should be option C. So now we discuss all the assignment problems, and I think here up to this uh, do not need to uh, explain further regarding this pre-consideration method, and all the doubts or all the important things I think we discuss is here, and I think I need to conclude our session, or we stop our session here now. So if we so by this we now our conclude our session, we stop here. It is already 8:15, and I think all the concept regarding the pre-consideration we discussed here, and no need to explain or elaborate it further regarding this pre-consideration. All the concept I think we cover here, and now we conclude our session, and all the recordings video should be shared to you through the NPTEL team, and also all the materials which is discussed here should be shared by the uh, NPTEL team through Google Drive. No need to worry. And by this, with this, I now stop our meeting. Um, wish you a very happy weekend, and thank you very much, everyone. Now I am closing my meeting. Thank you very much.